first question regarding the 400 kVA connected load and determining the demand load for the service is incomplete. To accurately calculate the demand load, you typically need to apply a demand factor to the connected load. This demand factor varies significantly based on the type of load and its usage patterns. Without knowing the specific types of loads connected, such as lighting, HVAC, motors, or receptacles, and without any historical data on how these loads are used, it's impossible to provide an accurate demand load calculation. The demand factor accounts for the fact that not all connected loads will operate at their maximum rating simultaneously. For example, a large office building might have a connected load of several hundred kVA, but the actual demand load at any given time might be significantly lower due to diversity in usage. To determine the demand load, you would typically refer to tables provided in the National Electrical Code, specifically Article 220, or consult with an electrical engineer who can analyze the building's usage patterns. These tables provide demand factors for various types of loads, allowing you to estimate the demand load based on the connected load and the expected usage. Without this information, the question cannot be answered definitively. The second question deals with calculating the general lighting and receptacle load for a 30,000 square foot bank. The calculation provided initially uses 3.5 volt-amps per square foot for general lighting and 1 volt-amp per square foot for receptacles. Multiplying 30,000 square feet by 3.5 volt-amps per square foot gives 105,000 volt-amps, or 105 kVA, for lighting. Multiplying 30,000 square feet by 1 volt-amp per square foot gives 30,000 volt-amps, or 30 kVA, for receptacles. Adding these two values together, 105 kVA plus 30 kVA, results in 135 kVA. However, since the choices provided are 123 kVA, 151 kVA, 162 kVA, and 173 kVA, none of them match the calculated value of 135 kVA. There are a few potential reasons for this discrepancy. Firstly, the question might contain an error, either in the given values or in the answer choices. It's possible that the volt-amps per square foot values for lighting or receptacles are different from what was provided. Secondly, there might be additional loads that were not specified in the question. For example, the bank might have specific requirements for additional lighting in certain areas, or it might have a higher concentration of receptacles in certain areas. These additional loads would need to be factored into the calculation. Thirdly, it's possible that the question is intended to test knowledge of specific code requirements or industry standards that would affect the load calculation. For example, the National Electrical Code provides specific requirements for receptacle spacing and load calculations in commercial buildings. It's important to consult the latest edition of the NEC and any applicable local codes to ensure that the load calculation is accurate and in compliance with all relevant regulations. To further analyze this discrepancy, let's consider some factors that might influence the load calculation. One factor is the type of lighting used in the bank. If the bank uses energy-efficient lighting, such as LED fixtures, the actual volt-amps per square foot for lighting might be lower than 3.5. This would reduce the overall load calculation. Another factor is the number and type of receptacles installed in the bank. The NEC provides specific requirements for receptacle spacing in commercial buildings, and these requirements can affect the overall receptacle load. Additionally, if the bank uses any specialized equipment that requires dedicated receptacles, such as computers, printers, or ATM, these loads would need to be added to the receptacle load calculation. It's also important to consider any applicable demand factors that might be applied to the lighting and receptacle loads. The NEC allows for demand factors to be applied to certain types of loads, which can reduce the overall demand load calculation. However, these demand factors are typically only applicable to larger installations and may not be applicable to a 30,000 square foot bank. To resolve the discrepancy between the calculated value of 135 kVA and the provided answer choices, it would be necessary to review the question carefully and ensure that all relevant information is included. It would also be helpful to consult with an electrical engineer or other qualified professional to verify the load calculation and ensure that it complies with all applicable codes and standards. In summary, while the initial calculation of 135 kVA appears to be correct based on the information provided, the discrepancy with the answer choices suggests that there might be additional factors or considerations that need to be taken into account. Further investigation is needed to determine the correct answer. Let's dive a bit deeper into the process of calculating electrical loads, particularly in the context of commercial buildings like banks. Accurately determining these loads is critical for ensuring the safety and reliability of the electrical system, as well as for optimizing energy efficiency. The first step in any load calculation is to identify all the connected loads within the building. This includes lighting, receptacles, HVAC equipment, motors, and any other electrical devices. For each load, you need to determine its volt-amp rating, which represents the amount of electrical power it consumes. This information is typically found on the equipment's nameplate or in its specifications. Once you have identified all the connected loads, you need to apply appropriate demand factors to account for the fact that not all loads will operate at their maximum rating simultaneously. Demand factors are typically expressed as a percentage and are based on the type of load and its expected usage patterns. The NEC provides tables of demand factors for various types of loads, which can be used as a starting point for your calculations. However, it's important to consider the specific characteristics of the building and its occupants when determining demand factors. For example, a bank might have a higher demand factor for lighting during business hours, but a lower demand factor during off hours. Similarly, a bank might have a higher demand factor for receptacles in areas where there are a lot of computers and other electronic devices. In addition to demand factors, you also need to consider any applicable diversity factors. Diversity factors account for the fact that different loads within the building might not operate at their maximum rating at the same time. For example, the lighting load might peak in the morning, while the HVAC load might peak in the afternoon. Diversity factors are typically expressed as a ratio and are based on the overall usage patterns of the building. Once you have applied demand factors and diversity factors, you can calculate the total demand load for the building. This represents the maximum amount of electrical power that the building is expected to draw at any given time. The demand load is used to size the service entrance equipment, such as the main circuit breaker, the service conductors, and the transformer. It's important to size the service entrance equipment correctly to ensure that it can handle the maximum demand load without overheating or causing voltage drops. In addition to the demand load, you also need to calculate the total connected load for the building. This represents the sum of all the individual load ratings without applying any demand factors or diversity factors. The connected load is used to determine the overall capacity of the electrical system and to ensure that there is sufficient capacity to accommodate future growth. It's important to note that the NEC provides specific requirements for load calculations in commercial buildings. These requirements are designed to ensure that the electrical system is safe and reliable, and that it can handle the expected load. It's important to consult the latest edition of the NEC and any applicable local codes to ensure that your load calculations are in compliance with all relevant regulations. Let's go through a more detailed example of how to calculate the electrical load for a bank. Assume the bank has a total floor area of 30,000 square feet, and that it is used primarily for office space and customer service areas. The bank has the following connected loads. Firstly, general lighting consisting of 1,000 LED fixtures, each with a rating of 30 volt amps. Secondly, receptacles, with an estimated 1,000 receptacles, each with a rating of 180 volt amps. Thirdly, HVAC equipment, with a total rating of 50 kVA. Fourthly, miscellaneous equipment, such as computers, printers, and AGM, with a total rating of 20 kVA. To calculate the general lighting load, we multiply the number of fixtures by the rating of each fixture. 1,000 fixtures times 30 volt amps per fixture equals 30,000 volt amps or 30 kVA. To calculate the receptacle load, we multiply the number of receptacles by the rating of each receptacle. 1000 receptacles times 180 volt-amps per receptacle equals 180,000 volt-amps or 180 kVA. To calculate the total connected load, we add up all the individual load ratings: 30 kVA for lighting, plus 180 kVA for receptacles, plus 50 kVA for HVAC, plus 20 kVA for miscellaneous equipment equals 280 kVA. To calculate the demand load, we need to apply appropriate demand factors to each load. For general lighting, the NEC allows a demand factor of 100% for the first 125 kVA and 125% for the remaining load. In this case, the lighting load is 30 kVA, so we apply a demand factor of 100%, resulting in a demand load of 30 kVA. For receptacles, the NEC allows a demand factor of 100% for the first 10 kVA and 50% for the remaining load. In this case, the receptacle load is 180 kVA, so we apply a demand factor of 100% to the first 10 kVA and 50% to the remaining 170 kVA, resulting in a demand load of 10 kVA plus 85 kVA equals 95 kVA. For HVAC equipment, we assume a demand factor of 85%, resulting in a demand load of 42.5 kVA. For miscellaneous equipment, we assume a demand factor of 75%, resulting in a demand load of 15 kVA. To calculate the total demand load, we add up all the individual demand loads: 30 kVA for lighting, plus 95 kVA for receptacles, plus 42.5 kVA for HVAC, plus 15 kVA for miscellaneous equipment equals 182.5 kVA. This represents the maximum amount of electrical power that the bank is expected to draw at any given time. Based on this demand load, we can size the service entrance equipment accordingly. For example, if the service voltage is 208 volts, we can calculate the service current by dividing the demand load by the voltage and a power factor. Assuming a power factor of 0.8, the service current would be 182.5 kVA divided by 208 volts times 0.8 equals approximately 1370 amps. Therefore, we would need to select service conductors in our main circuit breaker that are rated for at least 1370 amps. It's important to note that this is just an example, and the actual load calculation for a bank will vary depending on the specific characteristics of the building and its occupant. It's always recommended to consult with an electrical engineer or other qualified professional to ensure that the load calculation is accurate and in compliance with all applicable codes and standards. The calculation for the bank might need adjustments. For example, if the bank has a large data center or other energy-intensive equipment, the demand load could be significantly higher. Similarly, if the bank is located in an area with a hot climate, the HVAC load could be higher. It's important to consider all these factors when performing a load calculation. The NEC provides guidelines for receptacle spacing in commercial buildings. These guidelines are designed to ensure that there are sufficient receptacles to meet the needs of the occupants. The NEC also provides requirements for the types of receptacles that are required in certain areas, such as ground fault circuit, interrupter protected receptacles in wet locations. When calculating the receptacle load, it's important to consider these requirements and to ensure that the receptacle load is sufficient to meet the needs of the occupants. In addition to the NEC, there may be other local codes or regulations that affect the load calculation for a bank. It's important to consult with the local building department or electrical inspector to ensure that your load calculations are in compliance with all applicable codes and regulations. Performing an accurate load calculation is essential for ensuring the safety and reliability of the electrical system in a bank. By carefully considering all the connected loads, applying appropriate demand factors and diversity factors, and complying with all applicable codes and regulations, you can ensure that the electrical system is properly sized and that it can handle the expected load. This will help to prevent overloads, voltage drops, and other electrical problems, and it will also help to optimize energy efficiency. In the initial scenario, the calculation of 135 kVA might be a simplified estimate. Real-world electrical load calculations are often more complex and require a more detailed analysis of the building's electrical systems and usage patterns. Let's explore some additional factors and considerations that can influence the electrical load calculation for a commercial building. Firstly, the type of business or occupancy can significantly impact the electrical load. A bank, for example, might have different electrical needs than a retail store or an office building. Banks typically have a higher concentration of computers, ATM, and other electronic devices, which can increase the receptacle load. They might also have specialized lighting requirements for security purposes or for high lighting displays. Retail stores, on the other hand, might have higher lighting loads due to the need to illuminate merchandise displays. They might also have significant HVAC loads due to the need to maintain a comfortable temperature for customers. Office buildings typically have a mix of lighting, receptacle, and HVAC loads, but the specific requirements can vary depending on the type of businesses that occupy the building. Secondly, the size and layout of the building can also affect the electrical load. A larger building will generally have a higher electrical load than a smaller building. The layout of the building can also impact the load calculation. For example, a building with a lot of interior walls might require more lighting than a building with an open floor plan. Similarly, a building with a lot of windows might have a lower lighting load due to the availability of natural light. Thirdly, the type of electrical equipment used in the building can also affect the electrical load. Energy-efficient lighting, such as LED fixtures, can significantly reduce the lighting load compared to traditional incandescent or fluorescent fixtures. High-efficiency HVAC equipment can also reduce the HVAC load. The use of energy-efficient appliances and equipment can help to lower the overall electrical load for the building. Fourthly, the climate and weather conditions can also affect the electrical load. Buildings in hot climates will typically have higher HVAC loads due to the need to cool the building. Buildings in cold climates will have higher heating loads. The amount of sunlight can also affect the lighting load. Buildings in areas with a lot of sunlight might have lower lighting loads during the day. Fifthly, the occupancy patterns and usage habits of the building occupants can also influence the electrical load. Buildings that are occupied during the day will typically have high lighting and receptacle loads during those hours. Buildings that are occupied 24 hours a day will have a more consistent electrical load. The usage habits of the occupants can also affect the load. For example, if the occupants are diligent about turning off lights and equipment when they are not in use, the electrical load will be lower. Sixthly, the presence of any specialized equipment or processes can also significantly impact the electrical load. A bank might have a large data center or a server room, which can consume a significant amount of electrical power. A manufacturing facility might have heavy machinery or industrial processes that require a lot of electricity. These specialized loads need to be carefully considered when performing a load calculation. Given all these factors, it's important to approach electrical load calculations with a thorough and systematic approach. It's not enough to simply apply a few rules of thumb or to rely on simplified estimates. A detailed analysis of the building's electrical systems and usage patterns is essential for ensuring an accurate and reliable load calculation. This often involves working with electrical engineers, contractors, and other qualified professionals to gather the necessary information and to perform the calculations. The goal is to ensure that the electrical system is properly sized to meet the building's needs, while also optimizing energy efficiency and minimizing costs.